With example 36 in the book, what they're wanting us to do is take this function, f of x equals x cubed plus 8x squared plus bx, and find specifically values for a and b. For part A, we know for a fact that we want to have a local max at x equals -1, and then a local min at x equals 3. So remember, when we find these values of -1 and 3, what these really are values that make our derivative go to 0. Okay, so these right here would be the critical points that cause like f prime of x to equal 0. Okay, that's going to be our help whenever we're solving this problem. So obviously the first thing we want to do is find our first derivative. So f prime of x is going to be 3x squared plus 2ax plus b. Okay, so from there, if I set it equal to 0, and let's say I'm going to plug in the values individually. So the first time I'm going to plug in -1. So I have 3 times -1 squared plus 2a times -1 plus b. And the second time, I'm going to plug in my other one, my 3. So 3 times 3 squared plus 2a times 3 plus b. Okay. Now, this is a good thing because when I have my derivative the way it is, I have an x value, which is fine because I have x values, but I have two unknowns technically, a and b. So the only way I can solve for two unknowns is to have two equations that can help me solve for two unknowns. Well, equation 1 came from when I plugged x equals -1 in, and equation 2 is coming from then when I plug x equals 3. Okay, so if I write their equivalencies, then this is going to be basically 0 is equal to, looks like 3 minus 2a plus b. And on the second one, we'll get 0 is equal to 27 plus 6a plus b. Okay. Now my goal is to solve these two equations simultaneously. Just use back in your days of algebra, let's go back to there. Right away I know that if I multiply this top equation through by 6, and I'll get 0 is equal to, I'm sorry, not 6, but 3. My goal is to try to get the a's to cross out. So if I multiply that by 3, technically. Okay, so 3 times 3 is 9, minus 6a plus 3b. And then if I leave the second one the way it is, okay, then add these two guys up, I'll get 0 is equal to 36 plus 4b. And then solving out for b, we'll get a b value of -9. Okay, so there's part of our answer. They just want to know what b had to be in order for this scenario to happen. And now to figure out what a's got to be, you can just plug it into either one of the two equations and you'll be fine. So like to see 0 is equal to 3 minus 2a minus 9. So 0 is equal to -6 minus 2a. And solving that out, then we get a to be -3. Okay, so when a is -3 and b is -9, that I know for a fact, I have a max at -1 and a min at 3. And we are finished with that one. So let's do the same concept, but let's go on to part B. Well, part B asks us to do the exact same thing. We want to figure out what a and b have to be, and we have different conditions though this time. The first condition they give us is that the minimum value has to happen at x equals 4, and then the second part tells us that the point of inflection is going to be at x equals 1. Now, a minimum, remember, that's all going to come from information learned from the first derivative, but the point of inflection is all information that's going to be learned from the second derivative. So obviously then we also need the second derivative. So f double prime of x will just be 6x plus 2a. Okay, going from here, if I can easily get my a value by just looking at my second derivative. So when that is equal to 0, and what I'm going to plug in here is the x equals 1, because this is the one that goes to the second derivative. I'll get 6 times 1 plus 2a, and solving that out, then we get a equals -3. Okay, that was simple. So now let's go up to our first derivative. When that equals 0, and specifically when my x value is 4, because I have a minimum value, plus 2 times a times x, then all I have left to is find b. So let's simplify this out. 12 minus, let's see, 3 times 2 is -6 times 4. 24 plus b, and that'll give us, oh wait, real quick, I just caught myself. That should be a 4 squared. Okay, that's going to make a little bit of a difference. 3 times 4 squared minus 6, so minus 24 plus b. Okay, a little bit of difference there. So instead it'll be 48 minus 24. I'm glad I caught myself. And so then b is going to equal, by the time we do the rest of that, negative 24. Okay, box that up and we're finished with that problem. So on to the next one. With problem number 46, we basically have two springs, and each of them have a weight hanging down from them. And we have formulas S1 and S2. S1 representing the actual how far down that weight 1's holding, and then S2 for how far down that weight 2 is at. And in part A specifically, we want to know the times in the interval from 0 to t do the masses pass each other. Okay, so obviously when the masses are passing each other, then they're at the exact same height, so S1 needs to equal S2. Or plugging it in, 2 of sine t needs to equal sine of 2t. Okay, and they give us this nice little formula that can help us with when our angle is more than 2t. I don't know if y'all remember that from back in your trig days, but sine of 2t is the same thing as 2 sine t cosine t. So we just want to know the value of t that'll cause these two sides to be equal to each other. So if we move that term over, set it equal to 0 and factor out the common, 2 sine t, that'll leave us with 1 minus cosine t. Set that equal to 0. And so we're looking at when does 2 sine t equal 0 and when does basically cosine t equal 1. Okay. If you analyze this kind of closely, the sine value can only equal 0 at like 0, pi, 2 pi, and then cosine is going to equal 1 specifically only at 0, 2 pi, 4 pi. So really we're kind of talking about the exact same thing, aren't we, in both cases? T should be the same for both. So what we're going to do is we're going to say t is equal to k pi, or in other words where k is a constant, or t is going to equal any multiple of pi. And it would help if I write correctly, but t is going to equal any multiple of pi. Because for sure, all of the even multiples of pi will get cosine t to be 1. All the odds and evens will get sine to be 0. So either way, and since it says t can go from 0 to infinity, we're going to say any multiple of pi from 0 to infinity. Okay. So let's go on to part B. In part B, what they're asking for is, instead of saying when they're the distances equal to each other, so when they're the exact height, we want to know is when they're the largest apart from each other, and they give us a specific interval from 0 to 2 pi. Okay, so let's get a basic distance equation. Obviously the distance would be the difference between the two values. So let's say like S2 minus S1. How far down the second mass is from how far down the first one. By subtracting it will give us that middle area right between the two. Okay, and plugging in their values then, we'll get D is equal to, and I'll go ahead and write it out in their kind of the expanded form. So 2 sine t cosine t, and then minus S1, which is 2 sine t. Okay, from there, if I wanted to, I can go ahead and take the derivative as is, or I might clean it up a little bit, maybe see if that helps a little bit, and write it as 2 sine t, and then cosine t minus 1. Okay. Again, we want to find the derivative because it's asking us for the largest distance or the maximum distance. So we need the derivative to help declare if it's where the maximum distance is going to happen. And we're taking the derivative of the distance, so dd, with respect to time, so dt, and it's going to be the first, so 2 sine t, times the derivative of the second, which is negative sine t, plus the second, times the derivative of the first, which would be 2, and then the derivative of sine t is cosine t. Okay, going on and kind of cleaning this up just a little bit then. The derivative of the distance with respect to time will be a negative 2 sine squared t plus 2 cosine squared t minus 2 cosine t. Okay, now my goal is to solve this and set it equal to 0 so that way I can find my critical points. And when I see this, one of the first things I notice is the way I'm going to solve it is I need to have it all in one trig function. Okay, I know that I can replace sine squared t with, I know that cosine squared t plus sine squared t equals 1. So if I want to replace sine squared with cosine squared so that they're all in terms of cosine, let's do that. So the derivative of the distance with respect to time would be negative 2, replacing the sine squared with 1 minus cosine squared, plus 2 cosine squared t minus 2 cosine t. So having it all in the same trig function, that's going to help us factor it here in just a second. So dt is going to be negative 2 plus 2 cosine squared t plus 2 more cosine squared t minus 2 cosine t. Alright, and combining the like terms, so we'll have 4 cosine squared t minus 2 cosine t, and then minus 2. Okay, and again, we're going to set this equal to 0, so now we can find our critical points. Well, to help factor, they all have a common factor of 2, so let's go ahead and pull that out. Okay, and coming up over here on the right, let's finish factoring it. So we have 0 is equal to, looks like 2 cosine t and cosine t. The factors of negative 1 add up eventually to a negative 1 also in the middle. So let's put a minus 1 right there and a plus 1 right there. So it's asking us for when does cosine t equal negative 1/2 and when does cosine t equal positive 1. Okay. Well, cosine t is going to be positive 1 on the interval from 0 to 2 pi at just 0 and 2 pi. In that same interval, cosine t is going to be negative 1/2. Let's see, in quadrants 2 and 3, and it's going to be referenced to pi over 3, so there'll be 2 pi over 3 and 4 pi over 3. Okay, let's see if we got a little bit more room here. Yeah. Let's put these on the derivative interval. So we're going to look at d prime, the distance prime. And let's get on there. We have critical points of 0, 2 pi, and then we also have 2 pi over 3 and 4 pi over 3. Now, I don't know if y'all caught this though. But remember going back to the definition of critical points? Can critical points be endpoints? Because technically here at 0, we're at the very edge of our domain, and at 2 pi, we're at the very edge of our domain. And according to the definition for critical points, they can only be interior points. We can have local extrema at our endpoints, but we can't have critical points there. So really, I don't have to worry about these two guys. Our only potentials to find the, what we're trying to find the maximum distance, is that right? Let me check. Or we just want, yeah, the maximum distance. So we want to try to find a max value in there. Okay, so all we have to do is just test kind of around these two guys. Okay, so anything to the left of 2 pi over 3 that you can test, I mean, something simple would be pi over 2. Because pi over 2 is going to cause all the cosines to go away, and you just get negative 1, so obviously it's going to be negative right there. Between 2 pi over 3 and 4 pi over 3, you've got pi, and the cosine there is always going to be negative 1. So if I plug in negative 1, square it, times 2, so it'll be 2 minus a negative 1. So 2 plus 1 is 3, minus 1, that's definitely going to be positive right there. And last but not least, something between 4 pi over 3, you can do 3 pi over 2. That causes the cosines to go away, and just like that. Just something simple. Sometimes it's really easy. You don't even need to pull out your calculator to check it out. Okay, and we want to know the maximum value. When's that distance going to be the greatest? So we want a max. We're going to go from decreasing to increasing. So obviously that was a min right there. And to go from up to down, then we have a max right there. So looks like at t equals 4 pi over 3, we'll have a maximum distance. Alright, and looks like we're finished for that section.